Okay. Hey guys, hopefully everybody can hear me out there. We're getting ready to start the webinar. My name is Scott Keating. I am a product specialist here at SideFX Software, part of our WIKI group. And we have a guest, which is unusual for these webinars. It's Matt Estela. Hopefully you can see him as well somewhere on this side of your screen, maybe. He is an effects lead at Animal Logic, and he did an awesome presentation for us at SIGGRAPH, showing sort of these really cool non-VFX VFX, which we'll sort of get into a bit later. So welcome, Matt.
Hello.
So before we dive right into sort of showing the stuff that you're going to be doing, I want to mention to the people who are watching that we're probably going to save questions for the end, so feel free to ask questions along the way, and we'll sort of gather them up and we'll use them at the end or when there's time to ask questions, because there's a lot of really cool stuff to cover and we don't want to have to stop all the time, but we are going to answer questions. It's just probably going to happen towards the end of the presentation, if Matt is still up for that.
Mm-hmm.
So I guess just before we dive right in, I did have a question for you just about Houdini in general. So you've been in the industry for quite a while. Like, at what point did you actually start learning Houdini, and like what was it about it that made you interested in it?
Right. Well, I started learning it. Well, I was first sort of exposed to it back around version 2, I think, back in like probably the 2000, 2001. And I remember looking at it and thinking, this looks really interesting, but it was so, I guess, non-user friendly back then that I went, this isn't for me, and I ignored it. And then years later, when I went to Happy Feet at Dr. D, they were using Houdini there, but as I've said elsewhere, I was quite excited to learn it, and then found that in the department I was in at the time, which was lighting, we weren't really using Houdini in the way most people use it. We were using it as a very just thin wrapper, I guess, around the lighting pipeline. But in the process of trying to solve some problems we were having in lighting, occasionally I would walk around to the effects department and got friendly with a couple of those guys over there, including Michael Goldfarb, who now works at SideFX, and they would show me little tricks every now and then, and go, oh, that's quite cool, and quite a few of them, I think, wow, if I had to do that using Maya, I don't think I could. I'd have to go to R&D, I'd have to have a plugin written. So that was the first real seed of thinking, I like this. And then, but again, went back into lighting back at Animal Logic, which was all Maya based. But then last year, or the year before, I was asked to CD soup a couple of projects for Animal, which were primarily kind of holograms and motion graphic kind of stuff. And a couple of people had already started, and they were using Houdini. And that was Roger Franson, brilliant talented guy, Pavel, who's now gone somewhere else, and Matt Ed. And I don't think it was ever sort of explicitly said, but we just said, well, this all seems silly to try and take it outside of the package. Let's just leave it all in here. So I had a team of people who were all using Houdini, and I was meant to be in charge of them. And I thought, well, if I'm going to be doing this, I should try and learn the software. So cue a crazy sort of 3-month, 6-month cram session where I just hassled that poor team endlessly. How do I do this? How do I do that? What's the vibe? So went from knowing very, very little to being competent, I'd say, is probably the best way to describe it. The one thing that did sort of come out of all that, which I think has led to all of this kind of stuff, was because of my terrible short-term memory, whenever I learned a thing, I would have to write it down somewhere, and thought, well, I'll put it onto my website. And I was just collecting tips nonstop, and eventually I realized, oh, this is actually kind of a useful resource. So I shared it around, and suddenly it got really popular, and here we are. So, yeah, so I was aware of it for a long time. I only really started playing with it for maybe the last couple of years.
Well, that's great, though, because it's really cool stuff that you're going to show tonight. So the topic that we sort of proclaim is non-VFX VFX. So, well, I guess I'll let you describe like what does that actually mean?
Sure, sure. So again, one of the people that work with, actually most of the key players at Animal. So again, Roger Franson, Matt Ebb, Raphael Godot in particular, but mainly Matt, have a really strong sense of, yeah, you can do things using simulation, and you can do a complicated particle sim or a flip sim, but let's just see how far we can push a pure procedural solution for these kind of things. And so a lot of work for the early Avengers sort of prototyping for holograms and how we're going to visualize the internet and all that kind of stuff. My first impulse would always be, right, so we're going to need a particle system and crowds and flocking, and Matt would always go, whoa, hang on, let's just think about this for a bit. And he would go away and have a bit of a think and would come back with an amazing proof of concept render. And I go, that's amazing. So clearly that's like a crazy crowd system. And go, nope. And a lot of what I'm going to show here is basically all of his tricks. So just interesting sort of alternative ways of thinking about how you generate motion, how you analyze time, how you give the appearance of randomness or the appearance of some sort of self-aware intelligence to systems that isn't really there. It's just pushing things on curves, or it's just looping things over time. And if you can make it seem random enough and seem chaotic enough, you get all the visual complexity of a particle system or of a complicated dot system, but it's all virtually real time. So that you can scrub to any point on your timeline, and you get an instant update. You can make changes really quickly. You can have almost an interactive session with your art director or your VFX supervisor, and they go, oh, can we make it be calmer? And you go, yes, we can, and you have a slider for that. Or you can add sliders over time so that as the needs of the sequence or the shot progresses, you have a very clean sort of master control interface at the top of your Houdini session. And it's really sort of changed the way how I would approach most problems now. And so when I jumped across to Lego, and we moved to a bigger team, I've been sort of one of the few value adds that I can provide is to show other people who have come in from other studios and have all sort of immediately kind of reach for the simulate button. And again, I could say, whoa, let's just think of a nice sort of procedural way of doing this. And it's just fun. It's a nice way to kind of have a bit of a think about how you set things up and how to sort of maximize control. I quite enjoy it.
Yeah, I think that's like the most people's go-to with Houdini, because we have these, very sophisticated simulation tools. Is like, well, every solution is somehow a simulation. No matter whatever problem it is, we're going to simulate the answer to that problem. I think it's really cool that these examples that you're going to show give results that kind of look simulated, but are completely under your control. And like you said, I think it's really awesome to have sort of live feedback of what you're doing instead of the very hands-off kind of approach of a sim. Like you're going to run a sim and it might take 9 hours or something to do it, as opposed to like, well, what would that look like if it was 3 times as fast? And then you just do it. You know what I mean?
Exactly. And again, like, not to take away from doing sims. There's always a time for that. But I think people sometimes forget or take for granted all of the procedural systems inside Houdini, and probably don't use it to its full capacity. So that's what I want to try and talk about a bit with these little sessions.
All right. Well, I think we've probably delayed enough. I'm sure everybody in the chat is like, just show us Houdini. So feel free to. I think we're going to have to hand control over to you, and then we can maybe share your screen and dive right in.
Okay. Ready? So let's see. Do I push buttons or do you push buttons?
I'm not sure. We'll find out.
Oh, you tell me if you can see my screen. Oh, here we go. Show main screen. Yeah, show my screen. Okay. Can you see the screen yet?
There we go. Yeah, we can see everything.
Okay. I'm going to minimize that. Okay, so this is the demo that I was running for the SIGGRAPH booth. So what we have here, I just realized I probably should have stepped down to a non-retina resolution. Oh well. So what we have here is something sort of like a Prometheus hologram. I'll just show that one moving, which I think with a web streaming thing will probably not be great. But you can see this thing is a skittery hologram of a walking guy that looks all very dark and moody. Over here, we've got a setup which is, again, terrible on this, this dark display. Setup which is kind of like the Ultron hologram that we set up for Avengers. And over here, we have what I like to call the internet. So it's just boxes that slide around, sort of applying packets of data. It's all meant to look very sort of impressive and technical. And after all that sort of hologrammy stuff, I've got a little Lego car, just to show a bit of how we do some of our Lego stuff, which is actually sim-based, but well, this particular part will be sim-based, but don't tell anyone that. So going back to the Prometheus hologram. So this isn't exactly like the setup that was actually used in the films, but it's not dissimilar. And this is a demo Matt Ebb runs for people who are new to Houdini, and I thought it was such a great walkthrough. I thought I'd start with this one on the SIGGRAPH floor. So,
hey, Matt, just before you continue on, can you actually hit that green button there to maximize your screen? Can you do that?
Yes, I can.
Just to see if that will actually appear. Maybe.
Better, worse? That is now, that's a green button. So yeah. we're maximally maximized. Okay. Cool. I'll try and keep these icons nice and big so people can see it. What I'll do here, I'll see if I can make these dots a little bit bigger as well. Geometry, point size. There we are. Nice big dots. So here we have a walking hologram. It's all a bit skittish and sci-fi looking. And this little walkthrough, I think it's a nice demo of the kind of almost batteries included nature of Houdini. People often talk of Python being called the sort of batteries included programming language. I think of Houdini as the batteries included version of 3D. So what's quite nice about Houdini is that because it can do simulation and it can do crowds, there's a whole bunch of crowd motion cycles built into Houdini that you can repurpose for your own needs. So here I've pulled in one of the example bipeds. So this is just a chap walking along. For the amusement factor, you get a whole bunch of different animation styles. This is just the walking one, walking along. And what I've done here is I've turned off in-place animation so that rather than just walking on the spot, he walks through the scene. So Houdini has this concept of having containers or separate networks of things, which when you first use it, it's a little bit hard to follow. But once you do get used to it, it's a really nice way to keep related things encapsulated. So what I've got is this other work area here. So if I dive into this network, you can see that this is the entire setup to do this hologram technique. So it's a fairly small network. I think probably smaller than most people would expect coming from other packages. So if I go and look at this top node here, you can see that this is the guy. And what I've done is this is using an object merge node, and I'm telling it go up a folder and across to and then down to find the geo for the biped person. So I could browse this way. So here's a very outliner style interface. I can dive in and find the geo. Or if I know the path, I can use Unix style pathing to go up to folders across and down. So now I've got this chap here. I'm going to just bypass this node for a sec. I'll come back to it later. So the first thing that we're going to do for this hologram look is to take this solid geo and convert it into a random scattering of points. Houdini has a node for that, and it's called scatter. So if I view the scatter node, you can see that all this does is it takes incoming geometry and it just scatters points all over the surface. That's my kids about to go to school in the background there.
Houdini?
They are about to learn Houdini, yes. They're starting as interns any minute now. Second income for the house is good. So, so here you can see we've got this slider for the total amount, and even just this, I think people are often surprised coming from other packages how many you can push through Houdini, and it doesn't really break a sweat. So that's now pushing 10,000 points, and as I animate, you can see that's being recalculated on every frame, and it still plays in pretty much real time. 10,000 is a bit much. I'm going to go down to maybe about 2,000 or 3,000. So there you can see skittery jumpy hologram. If we zoom in really close, you can see that this is being recalculated every frame. So we're getting a different layout of points on every frame. Remember that fact for later. So the next thing that we need to do is we want to take this arrangement of points, which is sticking onto the surface of the walking man, and add a bit of variation to it. So a way to do that is using noise, and specifically we're going to use what's called a point plot or an attribute plot. So what I'll do, I'm going to make a new one off to the side here just to show how this works. So I'm going to tab and do point plot, and I'm going to get them together. Apologies for people who are familiar with Houdini. I just want to go a little bit slow for people who haven't used it much before, just to make all the steps nice and clear. So what we have here, now that I've dived inside this point plot, is a network that looks similar to a shading network in other packages that you might have seen, like say Maya or in Cinema 4D or Max. And so what we have here is this node represents a bunch of inputs on our geometry, and this represents a bunch of common outputs. So if you look over here, this is the geometry spreadsheet. And so what this is showing me is that for every point on this geometry, that's an entry in this spreadsheet, and it's showing me all of the associated attributes of that point. So if I were to go and find, say, point 0, which will be in this mess of points somewhere, let's say we'll find point, let's find a better one. Which will be easy to find. 276. So that point there. If I scroll down this list to point 276, right behind, what was there? 276. So there you can see that its position in world space is negative 0.2 on x, 1.3 on y, 0.04 on z, and it has an associated normal, which it's inherited from the solid geometry version, which is pointing off in that direction. So these attributes here, these are represented here on this input global as well. So there's P for position, there's N for normal, and if there were other attributes, other common attributes, they will be listed here. And there's other things that we can pull out from this setup as well. So there's the world time, as in the time slider in seconds. You can also pull out the frame, you can pull out the point number. You can do all these sort of useful things. So what we can do here, I'll zoom back out, turn off numbers, is I want to generate a noise function based upon each point's position. So if I hit tab and put down a turbulent noise, there's lots of different noise functions, but turbulent noise is one of the more fun ones. So the noise I'm going to drive by each point's position. So I'm going to connect P to the pos slider, and then I get an output of noise. Now what I want to do is I want to take this noise and I want to add it to each point's current position. So I'm going to put down an add block, and we're going to take the position, add some noise, and then feed that to the output position. So now with that, you can see that suddenly this this geometry has gone all noisy and lumpy. Now, if I go over here to the parameters for the turbulent noise, you can see I've got a whole bunch of sliders and values, so I can control noise. So first of all, by default, this is only outputting one channel of noise, whereas because this is a position, I want it to output noise on X, Y, and Z. So I'm going to change it from 1D noise to 3D noise, and that's that. Now you can see that compared to the rest position, that it's all tending to go up and to the side. And that's because this particular variation of turbulent noise, this alligator noise, outputs values between 0 and 1. Ideally, I want this to go between -1 and 1. If I look at the different noise types, you can see that I've got a zero-centered Perlin noise. That seems like a likely contender, so I'll switch to that. And now I can see that this is more centered around where the rest geo sits. And the last thing that I want to do is you can see that this noise is a bit too large scale or lumpy. I've got a frequency slider here, so I can change this frequency and I can add more noise. Now, what I might want to do is rather than having to dive inside this point pop each time I want to change the noise, I can take any of these parameters I want and I can expose them on the top of this network. So the way to do that is, so say I've got this frequency slider here, I can middle click on that and I can go parameter. So now, if I jump up a level, you can see that I've got this frequency slider up here instead. And that's essentially what I've done here with this one that I made earlier. So I've exposed the frequency and the offset. And what I've also done, if I dive into the one that I made earlier, so you can see here I've got a few more controls. The other thing I've done is I've taken the noise and I've run it through a multiply node, which is also being driven by a slider at the top. Now the reason for that is if I change those values back to say 1 on all axes, you can see that this has uniform noise in all directions, which is starting to lose the shape of the walking man. Whereas what I want to do is I want to have noise, say, going left to right on X, almost no noise vertically, and maybe a little bit of noise front to back. So I can use this scale noise slider. So I keep it 1 on X. I'm going to make it 0 on Y. So now any noise multiplied by 0 will give 0. So now you can see that all the vertical noise has been cancelled out. So I'll put it back to so that's at 1, that's at 0. And then I'm going to put a little bit of noise going front to back. So now this is a hologram that oops, turn off. That is mostly left to right based noise, which is looking a bit more interesting. Now, another nice feature about Houdini is the sense of modularity and this sort of node-based way of working. So once I've made this little control that has these sliders I want, I can literally just go copy-paste, so Control-C, Control-V, and I've got a new one. And then with this one, I can maybe make the noise go wider on that axis. And that's what I've done over here. So I've got one level of noise, which is a minimal amount of sideways spread. Second one that has a bit more. So that's now a level 3. And there's one over here that has a lot of noise. So that's the skittish noisy pattern sorted out. The next thing is this is a little bit hard to read. So once it's in motion, you can read it, but what it needs is a bit more of a sense of shading. So that's where we'll come back to this point pop that I bypassed earlier. So so if I dive into here, actually no, I'll make a new one. We'll start from scratch. So I'm going to look at this point pop and dive inside. So I was saying before that these are all the inputs, these are all the outputs. By default, it's sort of implied that the things that have the same name are just getting passed through straight away. So P to P, it does nothing. But what I can do is this attribute here labeled CD, that stands for color diffuse. So what I could do is I could connect each point's position and I could map it directly to its color. If I do that, you can see now that we've got this curious looking color version where you can see values get increasingly green the higher up it goes. And that's because the Y channel is being mapped to the green channel. So the higher it is in Y, the more green it is. But we can connect any attribute that we have into CD as well. We know that we also have normals here. So if we connect the normal into CD, then we get this this look that looks like a normal render, which you might recognize. Now, normals are vectors. So if I turn on display normals here and zoom in, you can see that the normal for each point it's a little arrowhead essentially, which points out and away from the surface. This is where we bring in a little bit of maths, and we can bring what's called a dot product. So what a dot product is it lets you compare vector directions. So hopefully the webcam is still turned on. And what it does is basically, if you have two vectors that are pointing the same way, it'll give you back a value of 1. If they're pointing perpendicular, you get a value of 0. If they're pointing in opposite directions, you get a value of -1. So what we're going to do here, we're going to put down a dot product. And we're going to use the normal as one input. And the vector that we're going to compare it to is already defined for us handily, which is to compare against 0 and 0. So basically comparing against a vector which points straight up. So if we connect that directly to CD, and I'll turn off normal display, we get this. So what's going on here is any normals which are pointing, which are starting to tend to point upwards, will get shades of grey leading up to a maximum value of white, and anything which is pointing perpendicular or down will be 0 or going into negative values, which, as a happy byproduct, gives us this sort of top-down shaded look. Now, because this is also going to be returning negative values, we want to clamp that off. So I'm going to put down a clamp up, which will just limit the values to between 0 and 1. And now we have this interesting, moodily shaded walking man.
Yeah, it's kind of interesting. Just to jump in here for a second, but it's kind of cool because what you've actually done there is more or less like a very simplified version of like a lighting pass, like a renderer might do. Exactly.
And there's a bit of niceness about this, which is something that, again, that Matt Ebb and Roger Hansen at work sort of showed me, which is that Houdini has this concept of a lot of reuse of concepts right throughout the system. And so the point bot was one of the first things that I learned. But then when I started to get into shading and making materials to pass to Mantra, I realized that shops and VOPs are actually done in an almost identical interface. And so what's quite nice is that all these very sort of abstract concepts about shading that I was a little bit wary of for a long time, in terms of we had a bunch of really clever shader writers at work, and they were doing tons of ridiculously cool stuff with normals and cross products and silly stuff. You can actually prototype them just using points and simple geometry in Houdini. And quite a lot of the time, once you can prove it works here, you can almost copy those nodes out of the point bot, paste them into a shader, and for a large amount of the time, it just works, which is really nice. So it's a good sort of, I guess, knowledge amplifier that you can start with simple concepts here, and then you can reuse them in lots of other parts of Houdini, which is quite nice.
That's awesome.
So moving on with this. So here we have this nice grayscale-looking thing, but we want to add some color. Well, if you know a bit of color theory, you would know that you can take a grayscale thing like this, and you can multiply it against a solid color, and you would get a colored version of this thing. So I'm going to put down a constant, and I'll change its type to be a color. I'm going to make that color a suitably sci-fi cyan, like that. Yep. Like that. And then I'm going to just multiply those two values together. So I'm going to take my cyan color, multiply it against our dot product, and feed that out to CD, and there we have spooky sci-fi walking man. Now, what I could do instead is, rather than use a constant like this, I could just promote that parameter. So now I've got the values up here, so I can drive it like that. But rather than do it through colors, I can tell Houdini, this vector here, this is meant to represent a color, so therefore show me this value as a color parameter that I can play with. So I can go up and I can edit the parameter interface for this thing, and I can find that value, which will be hiding down the bottom here. Oops. There it is. And I say, this is a color. There is color there, and hit accept. Now I've got a color slider, and I can even change the mode of this color slider, so I get a nice HSV based slider, which is pretty cool. And that's essentially what I've done here. So if I switch to the one I made earlier, you can see I've got a color slider, and I get Cyan Man. Now, the other aspect of Houdini that it's so built into the core of it that you almost stop thinking about it for a while is that you get used to this idea of nodes inheriting attributes from previous nodes. So if I go straight to the scatter node now, you can see that the scatter node also inherits the color. Because the input geometry has color, then these scattered points in its default state will basically inherit color as well. So here, on input attributes, it's got an asterisk in it by default, which means inherit any attributes you find, put it on these scattered points. So now if we go and follow down to the noise file will inherit the color as well. So now we're starting to build up this effect. So we have the little bit of noise, a bit more, a bit more. And I'm just going to bypass these guys for a sec. And another nice thing about Houdini that you get used to after a while is that similar to a compositing package like, say, Nuke, is you can just take almost arbitrary geometry and you can merge them together just as if you're merging layers in Nuke. So I've now got my small noise, medium noise, come on, large noise, suction, there we go. And I'm merging them all together down here with this merge block. So merge block, and there they are, all overlaid on each other. Now the one thing that I notice here is that with them all merged together at maximum intensity, it got a little bit hard to read. So what I wanted was to have the small amount of noise most visible, then the next one turned down a bit, and the outside one barely visible at all. So so Houdini has lots of attributes which it sort of understands by default, and one of them is alpha. So see how down here we've got the attributes that I spoke about before. So we've got the position, the color, the normal. And what I've done here with this node, which is called the point wrangle, is I've added another one called alpha. So Houdini lets you modify attributes on geometry in lots of ways. A VOP lets you do it in terms of this graphical node-based UI. What a wrangle does is it lets you do exactly the same thing, but in code. People initially are always a little bit scared and cautious of wrangles. I was for a long time. But what often happens is you'll start to use VOPs for lots of things, and then start to realize, actually, what I'm doing here in 5 nodes, if I could do that in code, it would probably just be one line, because it'll be, this value equals this plus this. And that's when you start to get into point wrangles, and once you start, they're like Skittles, M&Ms, methamphetamines. You can't stop. They're just hopelessly addictive things. So you put a 1 or 2 line bit of Vex, which is this language that's used in wrangles, 3 setups, and it's so useful and so quick. So what I've got here is I'm taking the color value and multiplying it by this slider. So sliders inside Houdini are called channels. So this is a channel labeled brightness, and that's what I've got down here. So now I can use this slider and I can turn the brightness up down. So I'm multiplying the color by that, and I'm also setting an alpha value based upon the same thing. So this first one, I'm keeping it maximum brightness. The second one over here, I'm setting its brightness down to 0.6, which you can probably barely see. I'll just try and boost it up a bit. So that's my first one. That's my second one at 0.6. And my last one over here is down at 0.3, so it's just barely visible. So now when they all get merged together, you get this nice staggered layout of skittish pointy values. So I might turn the outside one up a little bit. And now we've got this very controllable setup. So if the art director were to swing by and say, oh, it needs to be more points, less points, I can go back to the scatter and I can just turn down the number of points. If they said we want it to look more noisy, I can go to my noise values here and I can scale noise. So you can see that with this fairly minimal amount of nodes, we've got a very controllable setup, even to the point of if they say, actually, this hologram chap, he can't be walking anymore, he has to be sitting. Well, that's fine. Change it to a sitting state, and there he is. And that's the basis of that effect.
That's really cool. There's a couple of questions from some of the people in the chat. So Just wondering if you could maybe walk through the dot product once again, just to explain how you're doing
Yeah,
that.
sure. Okay. Let's see. So if I go into this one again. So so what we've got here is I'm taking, so for every point on the surface here, if I visualize the point normals, and I'll turn off the color version of this. Whoops, I'll do like that. Okay. So if we zoom in here, say just on this guy's head, this is visualizing the normals for each point. And so you can see that up here we've got normals that are pointing straight up. At the side of the head, they're pointing sideways, and say on his chin that they're pointing down. So the dot products, again, fantastically, amusingly described by friend cohort Matt Ebb, said the actual maths behind it is almost unimportant. It's for our needs in terms of how we use the stuff day to day. It's probably more important just to understand the end result. If you want to go and learn how this works under the hood, there's a whole bunch of YouTube tutorials of people next to whiteboards drawing things. But for us, all we really need to know about it is what the end result is. And all it does is it just lets you compare vector directions, and it just gives you back a value between 1 and -1. So again, if you have two vectors, say we had these two vectors here on the very top of the head, if we were to take the dot product of that normal and that normal, that would give back a value very close to 1, because they're pointing in mostly the same way. If we were to calculate the dot product between that normal and that normal, the value would be 0 because they're perpendicular. But if we were to compare the dot product between that normal and one down there, that gives a value of -1. So it just gives you the value between 1 and -1 to tell you which way two vectors are oriented relative to each other. So what we're doing here in this VOP is the first vector that we're comparing is a normal. That's wide from end to there. And the second one, if we were so inclined, I might even expose that as a parameter, so that way I can actually drive this directly from up here. So if I look here, I've now got this vector. So this is now comparing against a vector which is pointing straight up on y, 0, 1, 0. If I wanted to compare it against, say, on the x-axis, I could compare that against 1, 0, 0. So now you can see that this is giving me values of 1 for anything that the points along the x-axis. You can see the x-axis down there. If I wanted to compare it along z, that's now just showing us values of 1 where it's facing down z, or any value in between. So if I wanted to pick some sort of 45-degree angle, I can do a mixture of y and z, like that. So now you can see this is sort of a 3/4 top shading. Does that make sense?
Yeah, I think that's really good. And you can imagine, like, the dot product is one of those things. If you're have an art background as opposed to a math background, you find out about it, and then you just immediately start imagining like a million things you could use it for, like putting snow on. You know.
Exactly. And the other thing to kind of keep in mind is that over the years I'll have tried to get into learning about Renovan shading language, or about how to achieve other kinds of effects. And they'll mention dot products and cross products, and taking the normalized value of x, well, whatever it is, and it's all just a little bit too abstract, and it never quite sunk in. Whereas what's quite nice about playing with the stuff inside Houdini is that it's very immediate. You can see it, you can grab it, you can play around with it and go, well, what if I wire it this way? What if I switch that around? And it gives a much more intuitive sense for what these things do than you would otherwise get if you were just trying to do it purely in code, or just trying to write it in a very abstract, shadery way.
Yeah, it's kind of like a nice way of visualizing data, basically. Stuff that if you just look at the numbers of the dot product, it's very confusing. But when you see a character with shading on one side of its body, it becomes like, oh, that's very clear. I see what's happening there.
Exactly, and I think something else that Peter Claes mentioned at SIGGRAPH was the idea of if you having used Maya for a long, long time, I was very proficient in Maya, still am, I think. But I didn't quite get the fundamentals of 3D. So things like manipulating matrices, or what a normal really is, or what are the applications for a dot product or a cross product. They were sort of I knew that they were there, but I didn't really have a grasp honestly of what they were. And what's really nice is once you use Houdini for a bit, you definitely get a sense of now I understand these concepts that were always just a vague thing before, and so I think this just sort of bolsters your 3D generally, where you can sort of look at a matrix and go, oh, I know what that represents, or you can look at a vector and go, oh, I can kind of get an intuition for what that represents and what it does, and if I were to manipulate it in this way, this is kind of how it works. It's nice to get that sense of understanding. That's always seemed a little bit of a black art otherwise.
Yeah. Awesome.
Cool. Any more questions, or dive on to the next one?
Let's go on to the next one.
Ready? Okay. So we'll go away from that and go into tendrils. So when we were doing Avengers, the brief was basically do some cool holograms you haven't seen before. We had very sort of broad strokes of what the holograms should represent. So for the orange Jarvis hologram, they said familiar, rectilinear, complex, all these sort of keywords. And then for the Ultron hologram, they said it should be organic, a jellyfish crossed with an MRI scan. Blue was a keyword. Threatening, all these kind of vague words. So we just did so many tests and so many kind of iterations and look devs, and this was one of the things that we sort of came up with along the way. If I dive, I'll just let this play again. It's a little bit dark on this display. There we are. So you can see we've got the sense of curves, which are sort of pulsing and flowing along, and we've got what are meant to represent data packets flowing down those curves, as this very sort of jellyfish sort of aquatic life kind of vibe to it. And again, if I had sort of seen this off the bat without knowing the context, I would have said, oh, this must be some sort of amazing soft body simulation, and they've done loads of really heavy cloth soles on it to make it work. It's all procedural. It's all fake. So let's dive in. So to set this up, so the other, I guess, kind of remit to this is we had some concept art, and it was like just impossibly complicated, and very, very quickly we thought, well, you know what, we can't model that. We can't actually sit there and hand build thousands of curves in space. That's just going to take us forever, and if we get some sort of art direction change, we'll be in a really bad place. So again, we started to look into procedural ways of more or less growing it. And so this is one of the techniques, or similar to the techniques we used. So to start with, we start with a sphere. And so what I do here straight away is I assign some random colors. So another handy node within Houdini is this attribute randomize node. So what I've got here is I'm telling it to randomize this CD attribute, and now I get random colors all over the surface. And you can see that's represented down here in the spreadsheet. And then what I do straight away is I take this polygon surface, and I convert it into a fog, into a volume, essentially. So that's using this node VDB from polygons. So this node does what the name implies, that you give it any sort of polygon surface, and it'll convert it into a volume shape. And the volumes within Houdini, they have names generally. So the default name for a fog volume is density. So that's why that's called density there. Now what I've also done is I've asked it to make me a second volume. And that second volume I've called vel, short for velocity. And this one, I've asked it to get its attributes from the color. So this is a little bit vague in terms of, so what we have here is two volumes. One which represents the fog, this sort of gray thing, and another one which is mapping color into a volume called density. How can we see that? Well, if I just bypass this for a sec, actually I'll do some things off to the side. Houdini has lots of ways to visualize volumes to help you understand what's going on inside. So one way is I could just ask it to actually show me the colors of this volume. So if I put down a volume visualization, and I click that up, and I say, well, the density is density, and the diffuse field, essentially the color field, is vel. So now if we look at that, I boost up the exposure, you can see we've now got this ball of colored fog. Kind of interesting, kind of useless. What are some other ways that we can visualize these values? Well, another way is a volume slice. So I do a volume slice, and I do that. So here, turn that value. So here you can see this is overlaying both volumes together. So the red represents the density, and out here all these different colored bits. That's representing a slice through the volume, and it's showing me the vel field, and I can offset this slice through the volume to visualize what they're doing. That's kind of interesting. But there's another way, which is called volume trails. So if you imagine, going back to the vector and normal stuff that I was talking about before, that so before I had the normals, and you can visualize that with a little arrowhead. Well, imagine with this volume, if you could stick a little arrowhead at each point within volume, and I then encoded which direction the arrow faces based upon the color. So if it was just pure red, so say 1, 0, 0, it would just point the arrow down the x-axis. If it was 0, 1, 0, as in just as y, it would point straight up. And if it was 0, 0, 1, it would just point down z. So we can do that here with the volume trail. So if I put down, so the volume trail needs two things. It needs to be told where to actually stick these little arrowheads, or these little almost like sort of, I guess, flags or streamers in the wind, and then it needs to actually be told which volume to actually generate streamers for. So the first thing I'll do is I'll generate some points. So I'll put down another scatter node again. So if I connect a scatter to a volume, you can see that now scatters points throughout the volume, which is pretty cool. Then I'm going to put down a volume trail. And so this thing, so the first connection is the points, and the second connection is the volume. And you can see already that this is now generating me streamers to show me which way it thinks the volume is facing. In its default mode, it doesn't know which volume it should be visualizing, so I've got to tell it up here. So under velocity volumes, I'll tell it to point to the vel field. Now you can see that this is what those random colors represent. And we get this rather interesting looking swirly trail thing. And this already gives a clue of what's going to happen next, where you can see that these streamers are all again sort of trailing up and along X. But if we could make all these streamers face in towards the center, then that'd be the start of our sort of tendrily jellyfish effect. So what we're going to do is I'm going to do that with a volume block. So I'm going to modify the values of our vel volume, and then I'm going to run that to this volume trail, and we'll see what we get. So I'm going to dive into here. Let's have a look. So what we have here is a fairly simple network, where what I'm doing is the first thing I do is I generate noise. So just like before, I'm generating noise, and that gets re-output to vel again. So if I just do that one, nothing else, so I do multiply. So if I connect that volume to my trail, you can see that's what just noise. If I generate brand new noise and I connect it to my vel field, I get this is rather cool looking swirly messy thing. So that's step one. Step two is again, if a bit of vector maths, if you have two vectors and you subtract one from the other, what you get is a third vector that points from the end of one to the tip of the other, or is it the end of one to the tip of the other, something like that. Basically, you can take vectors and you can pull them back to point to a new direction. So what I've got here is I'm taking the position of each point in the voxel, and I'm essentially subtracting it from the volume, and then I'm writing it back out to my velocity field. And so I can control it. I'm pre-multiplying the position by a slider. So at the moment, I'm not using any of it. But if I start to turn this up, you can see what happens, that the whole system begins to untangle, and it all starts to point towards the center. And hey presto, we've got this tendrily looking shape. So at the moment, that's just too many points. That's a crazy amount of points. I'm going to turn down the amount of points that we're generating trails for. And you can see we get the basis of our shape. And what's quite nice here is that this turbulent noise, I've taken every single slider it offers us, and I've exposed them to the top here as sliders. And one of the sliders that it gives us is for offset. And the offset, rather than me sort of driving it by hand, I'm just driving it by time. So I'm literally saying that that the y offset will just equal the time slider. And what happens is, if you animate noise with time, you get this sort of pulsing, wobbly shape. And that's essentially the core of this setup. So what I got over here is the same thing, but dynamic. So here I'm scattering less points. This is 47 points. There's my volume block. And rather than use volume trail, which is fine, there is another node which is almost identical, but it just runs a little bit faster as your point count and your resolution gets higher, which is a VDB big vec points. It does pretty much the same thing. So if I look there, this is generating trails because I've got this output streamlines thing turned on, and now that thing bubbles about. So that's step one. Let's move on. So any questions so far?
There are a couple of questions, but I just want to point out a couple of things for people who maybe aren't super familiar with Houdini, is that if you go back to where you put down the volume VOP, over to the right there, for people who aren't aware, earlier you put down a point VOP,
Yes.
Even though when you dive inside it looks the same, you're actually operating on very different types of data.
Yes, sorry, I should have made that clear. So if you use the tab menu and just type VOP, you can see that there's actually quite a few different kinds of VOP networks. Most of these are actually the same one in disguise. So a point, a primitive, and a vertex VOP are actually the same thing, just with a convenient name and convenient preset setup. But a volume VOP is a dedicated one just for working on volumes, even though lots of the concepts within are very similar.
Yeah, I think that's sort of going back to the point you made earlier. It's very useful that, if you're learning how to use a point VOP, you're sort of automatically learning a lot of how to deal with volumes as well, because the underlying tools are basically the same.
Yep. Cool.
And just one more thing to mention just before you go on, sorry, is that I think it's really cool that you're using this volume trail node, which really is just meant as a way to help you visualize something. But since it outputs geometry, you can actually use it as an actual effect if you want, just because it's cool looking, basically.
Yeah, I do remember being quite pleasantly surprised the first time that I saw the volume trail. I thought, oh, this is cool, but it must just be some sort of OpenGL viewport thing. It can't be actual geometry, can it? And then I looked a bit closer and oh no, they are just actual curves, and I can go and do more things with it. It's fun to see that a lot of the tools within Houdini can be used for purposes for which they weren't originally designed for. And that's, I guess, sort of part of the fun is just sort of randomly kit bashing stuff together and going, what if I connect this to this? Oh, that works. That's fun. All right, so moving on. So we have these curves, but whereas over here the defaults for the volume trail is to give this sort of color-coded kind of peak graph showing you the start and end. I'm going to generate my own colors on these curves. So the first thing that we would likely do is we want some sort of UVs down these curves that we can map colors into. A handy trick with Houdini is that whenever you have curves or any sort of disconnected geometry like these things, if you put down a UV texture SOP and put it into rows and columns mode and attribute class in point mode, that will generate you UVs that start 0 at one end of the curve and 1 at the other. So if I look down here in attribute spreadsheet, you can see that I've got UVs down here, and these increase linearly from 0 down to 1 at the end, which is quite handy. So if I wanted to visualize that, there's several ways of doing that. So if I put down, say, a color stop, so color stop just adds a color attribute to a thing. So in its default state, it just adds a constant color, or you can make it to a random color. Or in this case, what I want is I want it to do color based upon an attribute. So if I do ramp from attribute, and I say the attribute is UV, you can see that this is now showing me this color ramp. And in fact, if I just show the red channel, you can see that it's 0, it's black at one end, and it's white at the other. So that's one thing. What I could also do is, rather than use a color stop, I could use a wrangle to do the same thing. So I'm going to put down a point wrangle, and I'm going to do so I'm going to change the color. So I'm going to be, say, CD equals, and just to start with, I might make it, say, red 100, just to show how that works. So that's for red. In this case, I want to make it be, say, the UV, so UV like that, and I get that back. In this case, I don't want the entire X, Y, and Z component of the UVs. I just want the first value. So to pull out one channel of a vector, there's several ways to do it in Vex. The laziest way that I know is just to go .x. So there'd be .x, .y, .z. This is just .x, the first component, and there it is. If I wanted to colorize that, I could take that and I could multiply that by color, just the same as we did before with the engineer hologram. So I can multiply that by, say, red. So there's now a red shaded version. But I don't want to keep typing code to do that. I want a nice color slider down there. So rather than use a vector directly, I'm going to use a channel. So I'm going to go channel, and I'm going to name my channel. I'm going to call it my color, like that. And what you get is, when you define a channel like this, you can press this little button here, and what that does is Houdini will scan the code. That's all right. Let me do that again. Delete all spare parameters. So rather than being a single value channel, I want it to be a vector channel. So I'll do CHV. And if I press a button, Houdini scans my Vex code and says, "Oh, you're referring to a channel. It doesn't exist. Let me make that for you." And so it makes it there. So now I can change colors like here. Again, like before, I would rather have an actual usable color slider. So I'm going to go edit the parameter interface, and I'm going to tell that thing to be a color slider. So I change the mode to color, accept. So now I've got this thing. So if you click on this little color wheel button there, you can change it into a HSV mode thing. So it's nice and quick to dial in the color I want. That's cool. But I want more than that. I want to be able to define a ramp of color. So as well as having ramps, I'm just going to comment this up a sec. As well as having just sliders for colors, Houdini also gives you sliders to define ramps, and the control for that is called ramp, the channel ramp. So I go that, so CD equals, and it's going to be a ramp called my ramp. And with a ramp, you tell it what is the attribute that drives it. In this case, it's going to be the first component of the UV, so UV.x. So so I've hit Command Enter or Control Enter on a PC to run it. Then I tell it to make the slider, and now I get this slider here. So if I expand that out. So now I can define the start and end points. I can raise the black point, which is all quite handy. But rather than just being a single value color ramp, I could define it, a single value scalar ramp or float ramp. I want it to be a full color ramp. So again, I can edit the parameter interface, and I choose my ramp, and I say, don't be a float ramp, be a color ramp, and accept. So now I get a color slider. So I can go to the endpoint, and I'm going to make the end color be that, and make the start color be nice purple. And so now you can see I've got this nice color ramp. And I can define any extra colors I want in the middle of the ramp. So I might make the middle bit the orange. That's two. I can move it around. That's all quite handy. But we can do more again. Let's see if do I do it in this step. Let's go cheat. Yeah, I'm doing more. So what I want to do here is I want these values to animate. So this introduces a bit of a trick, which is called modulo arithmetic, modulo math. So again, I had my own way of describing it. Matt, as always, had a better one, and he said basically modulo just means loop a value. So if I had say a value, so if I went my value is equal to time modulo 2. So modulo is the percent sign. So I do my value equals time modulo 2. What that does is that'll just loop every time it gets a 2, that'll reset to 0. So it goes 0, 1, 2, 0, 1, 2, 0, 1, 2 forever. So in this case, I could take that, and in terms of my UVs here, I could take my uv.x and add time to it. So now my UVs will be 0 to 1, but then I'm adding time so that they'll just basically increase forever. But then there'll be modulo so that they reset every 2 seconds back to 0, or in fact every 1 second, like that. Now, rather than do it in a separate value, I should be able to do this all in the one line. So I'm going to go for this value here, uv.x plus time modulo 1. So now, if I do it slow enough, you can see that I get the ramp is now sliding and animating through the curves. So that's going from the inside to the outside, which is the reverse of what I want. So rather than adding time, I'm going to subtract time. So make that u.x minus time modulo 1. So now they'll go from the outside in. That. What I actually want for this animation is to have a sense of a little pulse of light which is traveling from the outside in, and to have it multiple times. So I'm going to make that a bit more apparent by setting the first point in this curve to be black, the next point to be just the cyan, and I'm going to set up 3 pulses here. So I'm going to put another color there, another one there, back to black, bright again, like that, like that, like that. Just space them out a little bit more. So with this kind of thing. So now you can see we've got this kind of effect where now we have pulses of light which are zooming in. So this is all pretty cool, but ideally we don't want these all to be timed exactly together. We want these values to be slightly randomized per curve. So if I zoom in on this for a sec, and if I turn on point numbers, you can see that each point on these curves, it has its own number, 834, 881. But each curve itself, which is a primitive, also has its own number. So if I turn off point numbers and turn on primitive numbers, you can see that each curve is numbered. So 2, 8, 46, and they're all listed over here. If I change my spreadsheet view to primitives, you can see this is my list of curves, 0 to 46. So what I want to do, essentially, is I want to take the UVs, and if I could, for each curve, add a random number, a random offset, then they would all be pulsing at a slightly different offset. So we can do that. So what I'm going to do, just to make this a bit clearer, I'm going to define this with a new variable called, say, just u. So this is going to be the float attribute. So float u equals, and it's going to be uv.u to start with, sorry, uv.x, just to get started. So then I'm going to take u, and I'm going to add a random number to it, generated by each curve's number. So to do that, we could go rand, and the random function needs some input. In this case, it's going to be the primitive number, or at primnum. So now I'm adding u to that. Then I want to do our animation effects. So u is equal to u plus time, sorry, minus time, modulo 1. Put that in brackets just so it's all nice and neat. And then finally, with our city function, rather than being driven by that expression over there, we'll just throw it by u, which we just set up. And so now, with all that set up, you can see all the curves have their own offset of animation. So that's all set up. So I go to the actual one. Yeah, so here I've done the same thing, but I've just done it in place rather than doing it neatly like we've done over here, because I was panicked for time before. The other thing we can do is, again, we can give ourselves more controls. So here, where we're just using time unaffected, I can do time times a slider, and we'll call that slider speed. So time multiplied by ch speed. I turn that on. So now I've got a speed slider here. So if it's at 1, it moves at maximum speed. If I turn it right down to, say, 0.16, now they move nice and slowly. It's also pretty handy. That's what we've done on this side. That's it. That's all done. So that's how that's set up. Any questions about that a little bit?
Yeah, there are a bunch of questions. I don't know if we have time to actually go into them right now, but I do want I guess I'll just ask you, like a lot of the stuff that you're doing in the wrangle here, which uses Vex, and just to answer some of these questions, there's a lot of resources in the help documentation for Vex snippets, which is what this is here, a Vex snippet that shows the syntax and all that kind of stuff, as well as some resources for the Vex scripting language in general. But the thing I wanted to ask about here is, like, could you build this in an attribute VOP, for instance, if you're not comfortable
of course.
Writing snippets? Yeah.
Yeah. So let's see. Do I dare try and do that live?
Well, you can just say yes. You can do it. If you.
Well, I could just say it, but it's much more fun to actually try and do it. So let's see. So we'll go modulo, and we've got the UVs there. So I'm going to go. How are we doing? So it's UV and a ramp. So I bring in a ramp parameter, which in its default mode is color mode, which is good. So I'm going to go UV to that out to color. So the first thing I'm doing is I'm just taking the UV, feeding it to a ramp, and that's going out to CD. Now, we don't want the entire thing, we just want the first value. So I'm going to split this out. So I'm going to split this vector into floats. I'm going to go vector to float. So now I've got access to the X, Y, and Z components. So now I'm just using the first value, X to the ramp, and that out. So if I visualize that, you can see that that's now a ramp, exactly the same as we did before. So I'll change that color to cyan. Whoops. There's that. Now the next thing I'd do is I would be adding time to this. So I'm going to put down an add bot. And I'm going to add time. Come on, in you go. So I'm adding time and my UV there. And then I put in a modulo so that it stays within 0 to 1, and you can see that that's now doing the same thing. And then if I wanted to get the randomizing per thing, I can put down a random VOP, drive that by the primnum, which is that one there, and I can add that into there. So now we get the random slicing. There it is, live random demos. Does that make sense?
Yeah, that's awesome. And just to make this even more incredible, if you're even braver than you've already been, if
Yeah.
you go up, on that VOP node that you just made,
Oh,
and
and view the VEX code.
yeah,
Yeah, so something which is another kind of nice enabler to get into VEX is when you realize that VOPs are actually making you VEX code under the hood. So at any time, you can right-click on it and go view VEX code. And I mean, the code is often quite a little bit complicated to read because it's made by machines, but oftentimes you can just dive in and get an idea of what's going on. And so there you can see there's the modular function. That's where it's adding all of my values together. That's where it's making noise. It's a really nice way to start to learn stuff. So I definitely started using VOPs, and as over time, it's just a thing where you look at a thing like say that and go, okay, that's like eight or nine nodes versus doing it in 2 lines in VEX, and you start with just doing say 1 line in VEX, and then 2, and then 10, and then you start to put multiple wrangles together, and then you start to have a little library of cool tricks. So it's a very easy thing to get into that you can unlike say most other programming languages where you have to know quite a lot of stuff before you can do anything useful. With VEX, literally, you can get away with just doing a 1 line function, and it works great. And I think the other thing to keep in mind that separates VEX from, say, most other scripting languages like, say, Python or Mel is I remember when I first heard about these things, I went, yeah, it's basically the same as Mel. What's the advantage? The main thing, the huge thing is the performance. Mel is a scripting language. Python is a scripting language. As soon as you get up to non-trivial geometry counts with Mel, it slows down terribly. So you can use it to do kind of UI tricks or setup, but you wouldn't really want to embed it into live geometry like this. With VEX, here I've got it working on, how many points is this at the moment? This is 4,700 points. I could easily up that to 10,000, a million, 3 million, and Houdini would still run nearly real time. It's fast, it's compiled, you can do stuff that you just wouldn't think you could do if you're used to a Mel or a Python background. This is all essentially running shaders. It's live, multi-threaded compiled code, so it's super fast.
awesome. Thank you.
All right. So this last little bit. So next is the data packets moving down the code themselves. So let's see, do I have a? Yeah, I've got a little side note here. So loading up my favorite stock Houdini model, which is the pig. The ways in which I've taught this pig over the years, someone should call Petter. So here's a pig, and what I do here with a wrangle is I deform it in a horrible way. So here, what I'm doing is I'm setting up a few sliders. So speed, based on the speed slider, amplitude and frequency. And then I add to the x position of each point a sine function driven by frequency and speed, so that I get this wavy pig. Now, if I were to scatter points on that, like I do here, in its default state, you can see that as the pig animates, the points jump around everywhere. And that's because the scatter node in its default state doesn't keep track of the previous frame or the next frame. It's just as soon as it detects a change to the input geometry, it'll recalculate and it'll generate new points. But what if you didn't want that? What if you wanted the points to stick? Well, a simple way is to stop the input geometry moving. So here I put down a time shift node, which lets you move and slice and dice time on geometry. And I've said, lock yourself to frame 1 and nothing else. So now that this thing doesn't move, the points don't move, which kind of solves a problem, but doesn't really solve the problem. So what we want is we want to have these points stay where they are, but to deform with this wavy geometry. And so what we have here is a node that does that called an attribute interpolate. So what this does is on the scatter node, if I turn on these extra values here for source prim and source prim UV, each point now tracks what was the polygon that it was spawned on, and then here it tells you where on the polygon is the UV. So that's the source prim and the source prim UV. The attribute interpolate, what that does is it looks for source prim and source prim UV by default, and you tell it these are the points that are being scattered. This is the deforming geometry, and what this essentially does is for each point it looks up the primitive from here and the UV location on that prim, and it will move or basically interpolate whatever attributes you want to that position. So now if I look here, you can see that we've got these points that are sticking onto the pig. So that's handy. But what if we went the other way? What if, so this is basically static points and static UVs with moving geometry. What if we had moving geometry? Sorry, what if we had static geometry and moving UVs? What would happen? Well, that's what this setup is over here. So at this point, we've got our lines. Let's make it a bit brighter. And here, I've frozen it. So now it's a static version of these curves. I've scattered points on it. So I've scattered 80 points, and I've told it to store the source prim and the source prim UV. And here, I'm using an attribute interpolate based upon moving geometry, so that these points are now sticking to where they get birthed. But then here, in this wrangle, I'm doing a similar trick to what I just did for the color ramp, where I'm now taking the source prim UV and I'm animating it based on time and looping it every second. So I'll just go through this one by one. So I'm setting a time value. So basically here I'm saying time multiplied by a slider. So this is going to move at 0.3 of a second. Then I'm generating a random number between 0 and 1 based upon the point number. So they'll just get a new random number. Then I take that random number, which is going to be fixed and static, and I'm adding time to it. So now, so all these things will have a value between 0 and 1, and they'll be scattered in a random plot, and they'll all now just be shifting constantly with time. But each time they get to 1, they'll reset back to 0 and keep adding. But because I've got this random offset that they start with, they'll all be in this sort of scattered plot as they're moving along. And then, now that I've got that, I then feed that back into the source prim UV. In fact, I'm doing a little cheat there. I should be accurate and make it be actually set the first value, like that. So now that I've got moving, so now that each of these points has moving UVs, which you can see in the attribute spreadsheet here. So these are all linearly increasing. And if you look at, say, this one here, as that gets up to 1, it resets back to 0. So that's 0.91, 0.95, 0.97, and then 0. And it goes up again, and they'll get back to 1, reset to 0, reset to 0. So now that I'm feeding animated UVs and geometry to the attribute interpolate, that means that these things slide down the curves. And because I've got it all defined from this wrangle here, if I want them to go faster or slower, I can just change this speed slider to make it go faster or slower. So that's how I generate those base moving positions. Next thing I do is I take each of those positions and I copy a sphere onto those points. So here I've got a small sphere. I'll make it a little bit bigger so you can see it. So there's a ball. Whoop. That's better. And I'm copying that ball onto each of these points using a copy stop. So now I've got that. So these balls slide down. That's a bit big. Maybe back small again. Like that. Then I give those things a color. So this is like a bright white. You can barely see it because I'm boosting the color quite a lot. And then just like before, I'm just using a merge swap to bring these two bits back together. So there's my curves. There's my spheres. Merge them together. And there it is all moving. Any questions on that for the next one?
We've got some questions more about some of the under the hood stuff of Houdini. Somebody just wants to know the difference between saying, float and the name of an attribute and, at the name of the attribute.
How best to explain it? So let's start with, say, a grid. So if I go to a grid, you can see that, let's make it visible, and to the points. So you can see here that, that here, each of these points is just got one attribute, P, which is a vector which defines the vector's each point's position. If I put down a wrangle, and I want to define a new attribute for each point, as people have noticed, you can just refer to that using the at syntax. So if I wanted to make a new attribute just called foo, and I want to make it 1, I can just do at foo equals 1. And now you can see in the attribute spreadsheet here, we've got foo, and it's all set to 1. If I want it to be a random number per thing, I could do rand, and then the thing which is different per point is both the position or the actual point number. This column here, which is called PT num. So if I go back into here and I do rand based on PT num, you can see that now they all get random values based upon that. But if I were to do something like, say, there might be cases where to get an effect, I need a random number, but I don't need that random number to actually be stored with the geometry. That's when being able to define variables within wrangles comes in handy. So here, rather than having foo appear down here, I might say float foo equals this. So what happens there is this is setting up a variable that lives only inside the wrangle, and as soon as it's used, it's basically discarded. It's thrown away. So I might do then do something else based upon that number. So I might do, say, cd equals sign based on foo. I think that'll work. And now we get this. So this syntax is handy if you have intermediate things that you don't really need to be carrying down with you all the way down through the setup. So, like in this example here, I've got values for the speed, the amplitude, and the frequency, but I don't need those to be carrying through the setup at all. I mean, there's nothing to stop me doing it, so I could very well just have at speed equals that, and I change this to use at speed. But you can kind of imagine that beyond this thing, this is just a useless attribute hanging around, using up a bit of memory, making things look messy. We don't need it. It's true that you can put down an attribute delete stop, and I could say, actually, at this point, delete speed, and now it's gone. But if you know you don't need it at all outside of the context of your wrangle, you can just define them as essentially local variables, and then once they're used and they're gone, they're just gone. Does that make sense?
Yeah, that makes complete sense.
Cool. Whoop. Okay. Move on to the next example.
Yeah.
Yeah. Okay.
This is all very cool. Anytime I see that pig tortured, I'm happy. So.
Yeah, take that pig. Okay, so the internet. Now let's move on to turn off textures, turn off transparency. There we are. It's a bit easier to see this way. Okay, so here we have a system that the first time Madhav showed me a working version of this for vendors, I went, okay, clearly part of the system you're using schooling and flocking, all kinds of cool shit. And he went, nope, it's all procedural. And the core of it, if I dive inside it, is essentially one wrangle called, it was almost as simple as this. It was just called do SideFX. So it was a bunch of ramp controls and a tiny bit of code, and that was it. So if you look before the node, you can see it's just a block of points. And then after the node, you get all that crazy behavior. How did he do it? I remember pulling this apart and just being amazed at how, once you think in this sort of way, it's so powerful. And it just made me, this was the real kind of example that made me rethink how I approach Houdini, how I approach any sort of given task. So this is, so let's go through the preamble. So first we have a box. So Houdini has a few different ways to define a box. So normally when you make a box, it just makes a polygon box. Where's it going? Oh, it's huge, that's why. There it is. You make a polygon box. There, that's better. Is it? Yeah, better. Turn off the texturing, turn off geometry color. Oh, that's why. It's up here. It's there, it's better. Now see what's going on. So, so normally when you define a box, it's just as a polygon. You've got a bunch of options. So another is a polygon mesh that gives you subdivisions. What's going on there? Or another way is just to give it points, and that's what that is. And here I've gone one level again, where not just where I've told it not just to do points around the outside, but also to fill the inside with points as well. So I've got this big grid, this 3D cube of points. The next thing is a point VOP that does stuff to it. And what this one does is this is carving out chunks of points based on noise. And how it does this is pretty simple under the hood. So if we dive inside, you can see what we have here is again turbulent noise. Any point VOP that does anything worthy ultimately uses turbulent noise. So we generate noise, which is making a value between 0 and whatever. I think this is between 0 and 9. And I'm converting that to a integer. So whereas values might be, say, 0.2, 1.6, I'm just saying 0, 1, 2, whatever. And then I am comparing it. So this is this VOP essentially is a if statement, and it says if the first value coming in is true, this basically means not 0, send through the second value, otherwise send through the third value. So what's going on here is I'm testing noise, and if it's above a certain threshold, this will output the current point number. Otherwise, it outputs -1. Why do we do that? Well, we've got this other VOP called remove point, and what this does is if it's given a point number, so the actual ID of these points. So if this remove point VOP was given the number 304, then point 304 would be deleted. And so what's happening here is we're now deleting points based on noise. That's why we have this. I don't know if that's going to be easy to see in a streaming webcam view, but you can see we've got sort of chunks of points being taken out. And if it was so inclined, I could again promote parameters on the turbulent noise, so I could control the scale of the chunks, how many. I could control the gamma functions of it, so I could make it small holes or giant holes, all I control. But ultimately, we've got a cube of points that's been carved away. So that's part one. Part two is, so if this is my my main cube of points, here's almost the same thing. So it's a cube of the same dimensions, but it's got way less points. This has 4 points along each axis. So nothing special there. And I've got a wrangle here where I'm setting up a couple of extra attributes. So one is called cluster. And what I'm doing is I'm making cluster, this cluster attribute be the same as the point number. So there you can see with the first one, for point 0, cluster is 0. For point 5, the cluster is 5. The other thing I'm doing is I'm storing the point position, and I'm storing it as another attribute called P center. So again, same here. So this first point is at position -8.5, 8.5. P center is the same. Why? Why would I do this? Well, if I go and I take these ones, so these points and these points, these are both feeding into an attribute transfer. So what this does is this will transfer attributes from the right input onto the left input based upon proximity. So any points in this one, so say up in this quadrant here, that are close to that point there, will then inherit P center and cluster for that thing. A way to visualize that is using a color stop. So if I put down a color stop and put it into, make sure I've got color on. So if I, with the color stop, and I say, give me a random color based on an attribute, and the attribute is cluster, you can see now that what I've done is I basically defined little zones. So I've defined 4 zones on each axis, and there they all are. And I've also got P center stored per cluster. So how do we use all this to make, and literally go from that to the finished effect? Clearly there's some sort of magic going on. To describe this, I've got...
Sorry, just a heads up before you dive into this, because I know this might take a little bit. We've got about a half an hour left, just to give you a heads up about how much time is left.
Cool. I might finish with this one then and do maybe just a really quick 5-minute spin through of the Lego stuff, because it's just the show-offy thing.
Awesome.
But yeah, let's go through this. So to make this a bit easier to understand, I'm just going to look at one section up here. So here, with this blast up, I've said find all the points that have a cluster attribute of 12 and keep those and delete the rest. So this is another sort of handy thing that's just all throughout Houdini, that you can use attributes to control SOPs in all kinds of fun ways. So this is the 12th cluster. So what I have here, just because someone asked this before, is these are all mostly independent. So these all just kind of wide up directly from here into these. So these aren't necessarily cascading together, just in case people get confused. So this is just sort of showing the steps one at a time to get to the end result. So anyway, the first one here. So this first triangle, what I've got is I'm setting the position of each point, and I'm adding P minus the P center. So again, a bit of vector math at play here. If you have a vector, which say P, which is going from the origin out to where each point is, and then we've got P center, which here will be at the center of this box. And if I subtract one from the other, then that gives me a new vector, which points from that point to the center of this cube. So that's, and then what I can do is I can then multiply that by a slider, which is this expand slider, and I can take that whole thing and I can add it to P. So ultimately what that does is that gives me a slider that just expands the whole thing around the center point. So that's that. Rather than use a slider, like with the ramp examples before, I could use time. So here what I've done is I'm using a ramp that's based on time. But this ramp, what I'm doing is rather than going, say 0 to 1, I'm going 0 to 1 and then back to 0 again. And what that does is that means it goes out and in, like that, and that was cycle like that forever. Here is exactly the same thing, but I've modified the curve a little, so that what I do is I keep it locked at the start position for a bit, quickly ramp up, lock at the open position for a bit, and lock down. So it's still, then it's out, then it's down, out, down. So it's more of a steppy thing. So that's part one. Part two, slide along. So here, what I'm doing is I'm taking P, and just like before, I'm adding a vector to the position, but I'm adding the P center. So imagine that all these points, they share the same P center vector, which if you were to visualize it, would be an arrow going from the world origin out to where that is, and I'm just adding it to P, and I'm controlling it with a slider. So again, if I just slide it, then the whole thing moves towards and away the center. and I do exactly the same thing. So rather than use a slider, I use a ramp, and this time I've got a slightly different looking ramp where I go up quickly, hold there, and slide down. So it's out, down, out, down. So that's that one. Move down. Here, exactly the same thing, but I've now added the control to time just to slow it down a bit, so it's a bit more leisurely. Nice and slow. Oh, thank you. My lovely wife has just made me coffee. Thank you, Lucy. And so then when we get to here, this is combining both of the effects. So, the secret sauce is just in terms of how I time these two ramps. So if you look here, what's going on is I'm quickly expanding out so that it's a big thing. Then I slide it along to the outer position. Then and then here it then contracts again to its small size, but it stays away. Then I expand it out again, slide down, contract. So just by kind of roughly lining up these curve positions, you can see that I get this out, slide, contract, out, slide, contract. So that's all that effect. Now if I disable this blast node, so I turn everything back on, we can see that now they all do the same thing, outside contract, outside contract. Now, this is almost there. The only thing we would need now is to make sure that these things are randomized in time. And if you remember from the earlier example where I did a random number based on each curve's primitive number, then they all got a random color ramp offset. Well, here, if I had some attribute that was basically unique per chunk, and I made a random number based off that, then they would all get a different time offset. We have that attribute. It's the cluster attribute. So if I go into here, the only difference between here and the final example is this speed line here, where in the last example, I take time and I multiply it by speed, but I add a random number based on cluster. And I'm also multiplying that by a slider. So if I set this randomized slider down to 0, they all move in and out at the same rate. But if I start to add this random number, then they all start to get their own offsets. And that is the core of the effect. So I can now look at this thing and you get this cool in-out slide effect. And the only thing left to do there is for each point, I copy a cube onto each point. And there you go, that's the internet.
I think it's really interesting that like the core of this effect is almost the same as the last effect, but it gives you a completely different look.
Yeah, exactly. And I think a lot of my canoodlings on my my website tend to fall back onto these very sort of lazy tricks of you take time, you slice it up with a modulo, or you run time through a sine wave, or you drive a random value based on time, and make things do things based upon time being sliced in different ways, and you can get all kinds of very cool effects.
Yeah, once you start offsetting all the different pieces, the overall effect starts to appear like much more organic and randomized than what you would expect from driving it all off of one parameter, essentially.
Yeah, exactly. Again, this is turning into the Meta fan club session, but one thing that he said to me early on, because I kept sort of defaulting to go to just pops or silver sops and all kinds of simulation tools, and he had a really good way of approaching it, which is to say, well, imagine you didn't have Houdini. Imagine you just had sort of just like the ability to keyframe and nothing else. If you could keyframe it, could you keyframe it? And I think about this kind of thing and go, well, yeah, if I kind of rethink the problem so that I just had a whole bunch of keyframes and I set the whole thing up so that it was all moving together, and then at the very last step, I were to grab all of my keyframes and I just offset them randomly in time, so somewhat early, somewhat later, you would get that effect. You say, well, if you can rethink a problem in those terms, then you don't need simulation. You can start going down these paths. And it's always been a really nice little challenge just to never know how sort of big or simple the effect. You go, well, how would I approach this in a procedural way rather than in a simulation way? It's a nice little mental exercise.
Yeah,
so
it's a really excellent way to think about it. I've never heard that before, but that's a really good way to state that problem, I think.
Yeah. And then let's move. Do you want to answer some questions about this, or move on to the last one, and then we'll do a little question session?
Well, let's save it for the end.
Okay, cool. All right, so last one, which is just showing off a bit of Lego stuff, which completely ignores everything that I've just talked about in terms of proceduralism, and it's just a fun sim example. But just to show how we kind of approach our stuff at Animal. So if I go and check out this this van, which is one of the vans from the first Lego movie, what we do on our side is points. We actually represent all of our Lego models within Animal as points. So so here I've just kind of baked out some of these levels, and so here you can see this is generally what we work with, and you can see each brick is a point, and each point has lots of attributes. So there's things like the important ones is the part ID there, which tells you which brick it is, and the material ID, which tells you what color it is, and a bunch of other stuff that we sometimes use, sometimes don't. So there's the orient, obviously, some connectivity information, its visibility state, all kinds of jazz. What is kind of fun about this that I didn't realize until rather late in the game is these are part numbers that we list here. These are the actual proper Lego part numbers. So say this one here, 34488. You can go to the internet and so I have a window. There it is. You can type in Lego part 4488, and you actually get what that part actually is. So it's a fun way for us to research parts and to just go, what's a fun part that all the kids are using these days? Oh, it's part 4488. That's nice to know. And so what we do is we take that and essentially using the instancer and the copy stop, we have a library of the actual sort of geometric versions of these bricks, and it just replaces each point with the actual Lego brick form of that. So that are there. We also have several levels of detail for these. So this is getting close to the renderable version. But we also have a sim version, so we can swap between them as we want. So these are convex hull versions of these things, which I believe we took out of LDD. So early on for Lego, we were looking at what was the most efficient way to model Lego, and in the end, they worked out the most efficient way was to use the free app Lego Make, which is designed for 10-year-olds, called LDD, Lego Digital Designer. And I just love the idea that we have, like senior modelers with, X years of experience, getting paid lots of money, spending all day in a tool designed for 10-year-olds. And I believe because Lego were super helpful with us, they gave us access to lots of the underlying tech behind LDD. And one of it is that LDD has its own sort of simple physics simulation, so that when you try and click bricks together, it knows how they should react and how they should stand. And we thought, oh, that will be quite nice for doing sims. And so we can pull that into Houdini, which is quite handy. So these get pulled in as packed prims. And you can see that if I do a exploded view, that it's a full actual factual working Lego model. And we can feed these directly into Houdini's bullets packed prim system. So I can take these things and using a wrangle, I can set some sort of initial velocity, feed that to a .NET, and I can explode them. And we came up with a bunch of really nice systems so that reading a lot of the information provided on the bricks by Lego, especially the connectivity information. We can make little glue networks to pre-bind things together, which should be bound, or we can sort of pre-fracture them where we feel it will be funny to see kind of a crack at that point. So we can get really nice-looking sort of chunks of models will fall apart and crack, and we can set more states in them. It's going to be fun. And then we will take that and we'll convert that back into points, and we will then feed that down to the rest of the pipeline. Or in this case, I might take the render geo and the simulation geo, and I'll transfer the sim movement back onto the render pieces, and we get renderable Lego. So that's my little 30-second teaser for how we do Lego at Animal. All right, so it's 9:46, and I should be getting to work. But let's do a quick Q&A if there's any questions.
Yeah, for sure. I'll pull over. Let's just go through a couple of the ones that have been piling up during the talk.
Sure.
Let me see if I can find something. So I think you actually already sort of answered this, but somebody was wondering if you could create sort of things that go back and forth. So instead of going from 0 to 1 and then back to 0, to go from 0 to 1 and then backwards from 0.9, 0.8 back to 0.
The ramp is probably the best way to do that.
Mm-hmm. I think you already answered this as well, but somebody was wondering, like, so how long you've actually been using Houdini to the point where you felt comfortable actually like digging into these networks and understanding what's going on there.
Yeah, I was conversant, I guess, within about 3 months. And not that I'm amazing by any means, but I have used Maya for quite a while, and I've been a dangerous level scripted coder, so I understand just enough Python that it can be properly dangerous in a pipeline. But this level stuff, it all clicked really quickly, and I think again because you can start coding VEX quickly without a lot of the boilerplate stuff that you would need to do if you were doing it in, say, like even JavaScript or processing or or Python. You can just literally the one line to make things move. You can just put that into a wrangle and it works. So you can get up to speed more quickly in Houdini than I think you can in other systems. So yeah, I reckon I was up to speed within a few months, but to get sort of like cocky and confident, false confident in the way that I am now, it's probably about a year, I think.
Yeah, that's not bad. Did you find that there was a lot of knowledge transfer that you could take, your CG knowledge from other software and apply it, or was it sort of like starting over again?
Yeah, no, there was. Let's see. Probably the thing that was the most useful background knowledge was probably compositing in Nuke. That way of working with things in terms of like a very sort of clean node flow. This feeds to that. This node is merging these two things together. That was the most direct analogy. Maya, I was doing sort of mildly show-offy hypershade networks and things. That was also useful. But also, I think just I had been doing this now since 2000, 2001. So little bits of everything all sort of came together, and I could definitely see, oh, that's like a thing in Cinema 4D I used one time, and that thing's like in Max, and that's like in blah. It was lots of sort of general concepts that have been floating around, and suddenly they were made very concrete in Houdini and very consistent. So any sort of prior knowledge is good. I would say though that there's generally a what's the word? Stereotype? No, that's not a word. An idea that Houdini is too hard to start with. That it's only for kind of advanced people. I think the opposite way. I think because the interface is so clean and minimal, and things you learn in one module, one way, end up being reused everywhere. I've taught a couple of people from scratch using Houdini, and they seem to get up to speed more quickly in this than they do in other packages. There's so many caveats in, say, start with this, but don't do that in this module. But this thing is a whole other module again, so you've got to relearn everything. Whereas Houdini is very consistent, which I like.
So I guess we're close to wrapping up. So like a question maybe just to end off is, do you have any advice for people who maybe like watch this and they're new to Houdini? And a lot of this, even though you did a very good job of explaining it, is probably a little bit overwhelming for somebody who knows nothing about Houdini. Do you have any advice for how to get started? Like where should you dig in first, and maybe like things not to dig into until you're more.
Sure. I mean, definitely, I think the Go procedural videos are pretty good just to get started. In terms of like actual modules within Houdini, I think just staying in SOPs for as long as you can, for as much as you can, is a good way. Like, because I think if you get a really solid grounding in SOPs, everything else flows much more easily. The Intagma videos are fantastic. They just explain these concepts in such a clear way, and they produce such beautiful results. They're really, really good. It's like, and it's been funny where you see each time those guys put out a video, and then about a week later you see a raft of Vimeo things of everyone copying the same effects, where obviously the way that they're teaching us stuff is just really kind of resonating with people, which is fantastic. Odd Force is great for questions and answers. The SideFX forums, I'll give a little plug to my own site, which you probably know about. So the main sort of thing that I was doing a lot of was as I was learning all these things from the people at Animal and from the forums especially, because I've got such a terrible short-term memory, I would just write them down. And so each time I learned a trick, I would put it on my site, and at my peak, I was doing 2 or 3, 4 cool tricks a day. Right, I've got to write it down, and it became a little exercise. Like sort of doing stuff or something where every day I'd go home and go, right, how do I condense that one lesson down into a really clean, minimal example with an animated GIF, and that's what sort of ended up here. So now I've got all these sort of silly examples and film and personal learning. That's a fun one. Yeah, people seem to kind of respond to this pretty well, because it does. It's this page especially. It's a fairly linear thing where it starts from kind of absolute first principles. How do you transfer position and color on things, right through to at the very end. How do you do sort of cheating flocking systems and crowds, and how do you march cubes along? How do you do these kind of silly, primitive fiddly effects? I've had quite a few people say, I was kind of floundering a bit inside Houdini, but I found this site and it kind of made it all kind of colorless. So yeah, go here, ask me questions. I'm pretty much on both forums 24 hours a day, much to the disappointment of my wife and children. But yeah, I mean, I'm still in this sort of slightly obsessive mode in terms of Houdini, where if I'm not using it, I'm thinking about it. I'm trying to think of, how would I do this effect? How would I do? Oh my God! No, I have to run away from the TV and start to play around. It does, once you realize that it can become a sketch pad for just general ideas, and you can just mess around with it. And that's kind of the main thing. Again, like if you're getting into sort of advanced and cloth stuff or rigging stuff, you kind of get to a certain point where you can't tinker with it anymore. It's too complicated wiring under the hood for you to mess with. But with Houdini, like with Nuke, even with super complicated networks, you can get to the very end and go, well, what if I swap around these two nodes? What if I put that there instead? What if I bypass this? What if I put down another thing? And you just learn by just breaking things. It's that's my method. I just put down random nodes, break things.
Yeah. I think the great thing about the examples that you provided and built are that they're all cool looking. So like you always come out of it with something that's pretty neat, as opposed to like just learning about what the dot product is. mathematically, you go, well, this is how you use the dot product to make a cool hologram.
Yeah, and again, I think Matt Ed's background as a designer means he's always able to come up with a really sexy result, and I kind of aspire to make results that are that nice. Don't often achieve it, but if all else fails, I just take the pig and do horrible things to it.
That's awesome. So I guess we're pretty much out of time here. I want to thank you for all your time. That was really awesome. You went through a ton of stuff there, and I hope the people on the chat got some good information out of there. I know it's early. You said you're going to work, so good luck at work today.
Thank you very much. It's now nearly 5 to 10, so I should probably get in.
So yeah, once again, my name is Scott Keating. I'm a product specialist here at SideFX Software. You'll often see me at SideFX events, so come and say hello if you see me standing around. And thank you all for watching, and of course thank Matt for going through all the trouble that he went through. And I guess good night or good morning, depending on where you are.
All right.
All right, thank you.